Okay, so the recording is started and I hope the screen is visible. Right? You're able to see the screen?
Yes, ma'am.
Yes. Okay, so yeah, coming back to where to our discussion yesterday. So we were sorry. So we were talking of these adversarial games, this adversarial search more precisely. So where you had a max agent and a min agent, and we kind of saw this algorithm yesterday, and like how you compute the value of each of the states, where the min agent is trying to minimize his utility. Maximize his utility, and thereby it becomes minimizing the max agent's utility. So that is our utility. The min agent is trying to minimize, okay? And the max agent is trying to take an action, which as a response to this, anticipating that the min agent will hurt him. Okay, so we wrote the algorithm. So one thing I just wanted to state is that in this algorithm that we wrote, we mainly focused on computing the value of each state, right? Actually, what happens is ultimately you're interested in what is the strategy that you should take. So for this example, yes, the values you compute, but ultimately what you want is this action A2 for at the state S1, the max agent should take the action A2. So that is the ultimate result you want. So our algorithm just returned the values of the states. So additionally, you should also do an arg max operation. So out of all the states, right, what is the maximum value? So out of all these successor states, what is the best action? Right? Of course, the best value you have, and you also have to return this action. Okay, so that's something which I didn't explicitly write, but in your implementations, you have to also take care of that. Okay, so in the process, there might be some changes to this algorithm may not be like exactly implementable in that sense, but yeah, I hope you get the idea what we're trying to do. And also another thing is you can have like multiple agents. So now here what we have written is uh, where you have two agents, but you can have like maybe you have two max agents and one min agent. So totally three agents are there, and they play like the first player is a max player. So this is a max one, and the second player is the min player, and here this is the second max player. So such things can also happen. You can have different combinations. So you can actually adapt this to consider the particular order. So the only thing is that the order in which they play, that has to be fixed beforehand, and then you can extend the same algorithms to other cases. So in fact, your next labs, right, the second labs is there you will have like multiple agents. So there'll be like one max agent, so that's Pac-Man, and multiple ghosts, right? So the ghosts are all min agents. So there's a particular order in which the ghosts will play. Okay, so you'll have to adapt this algorithm for that setting, but it's not too hard. It's the ideas are essentially the same. Okay. So as a homework, I will also like you to try. I mean, take any just try a random example, like draw this kind of a tree, but do multiple levels, maybe multiple agents, and fix some arbitrary utility values and see how the algorithm would work. Okay. Right. And then we said that, the tree can grow like very large because there are a lot of actions, and I mean, the state space itself can be very big. Okay. And we were looking at what are the schemes that you use in that kind of scenarios. Okay. And that's when one possible idea was to do, cutting off the tree at some depth, and you just use you just pretend as if the tree is this big only, and now you need to assign some kind of values to these intermediate states. Those are actually intermediate states, but you're behaving as if that's a terminal state. So you need to assign some notion of utilities here, and that brought us to evaluation functions. Okay, so the idea of cutting off the depth is like you're traveling on a road, and you have your headlights. Okay, and there is some depth up to which you see. Okay, at some point of the road you will see till there, and then once you get there, you'll again your headlights will see a bit further. right? So it's the same idea. So at this stage, when you start off here, you assume the tree is this big, the squared portion, the part which I've circled in some sense. Okay, so you assume the tree is this big, and then you take the best action. Now, once you come to this, once the tree is at this stage, right? One of these actions are active. One of these actions have been taken, and maybe it's this state that you have reached. So now the tree is a little bigger, right? So now the same depth. So if you fix the depth as, say, in this case, it was 3. So the depth was 3. Now, once you take the next level, you can see a little more further, right? You can see one more level down, and you will assign terminal utilities to this level. Okay, so it proceeds in that way. Okay. So I just wanted to make this point also clear. I was not sure whether I told you this. Okay, and we saw some ways in which you can write evaluation functions. It's all dependent on the problem you're trying to solve. And for if the terminal utility is high, as it goes closer to the terminal utilities, it should reflect that point. Okay, so the evaluation function is high when that state is closer to the desirable state. Okay, so that is something which you want. That's a tip in designing of evaluation functions. And we also saw these weights that you can assign to think of what is the importance you want for each of these features. Okay, so these are like some end features you have, and this is entirely up to you. You can decide what is the kind of features you want, and if you have, depending on the features you have, you will have a nicer model, and you will have a better and better search tree. Okay, so yeah, so this is about evaluation functions that we discussed yesterday. Now. Yesterday when we were talking what are the other possibilities of improving the search space, like improving the complexity of the search, there was one more idea, right, about I think it was Deep Desai who mentioned that you can if you know already that some part of the tree is bad, right, you don't even have to get into that part, right? So that's an idea that we will explore today. Okay, so let me just start a new page. Yeah, so this is what we'll discuss today is called, it's this idea called alpha beta pruning. So pruning is just where you disregard some parts of the tree. Okay, and that's what this is going to be. Okay, so maybe like let me just start with an example itself. So maybe again like 2 deaths. So okay, so maybe you have like 3 children. So yeah, so maybe these are the terminal utilities. 3, 12, 8. Maybe this is 2, 5, 1. This is from the Russell Novick book, more or less. Yeah. Okay, so 14, 5, 2. Okay, so this is now a search tree, and this is the max. The first is a max player, and the second is a min player who is going to play. Okay, so what is going to be like from this node, right? So let me label them also: A, B, C, D. Okay, so yeah, A, B, C, D, and maybe the actions I'll call it like A1, A2, A3. Let us just make it A1, A2, A3 everywhere. Okay. A2, A3. Okay, so now, suppose we are trying to backtrack, right? Like we start off with, if you're doing a min-max algorithm, you start off with A, and then you try to explore down into the tree. Okay, so this I'm considering there is no pruning. I mean, there is no depth limitation. I mean, there's a pruning going to happen, but you're not doing any depth limited search. Okay, so this is the entire tree that you're going to consider, and at B, what's going to happen? The min agent is going to choose the lowest of these 3. So what's it going to do? Which is the best action for at B?
A1.
A1, right? A1, and with a value of 3. Okay, so now after this, what's going to happen is the max agent is going to come to this node C. Okay, so it's going to explore what happens in state C. So here, what's going to be the value of this at state C?
One.
1, right? So how, if you think of how we found that 1 is the best, we started exploring each of these nodes, right? So we came here, we say that okay, 2 is the current best. Now you explored 5 and you said that okay, 5 is not lower than 2, so skip 5, and then you go to 1 and then you say 1 is less than the best explored, which is 2, and then you conclude that it's 1. Okay, but now actually one thing, when you look at the max player's perspective, what's going to happen is he's found one branch, this branch A1, um, right, the one here which I've now put in red, which is giving you a value of 3. Okay? And at the stage when he's going to look at each of these nodes, so when he comes to C, he sees that you have a utility of 2. Okay, so the min agent, whatever it does further down the tree, the value of this node is going to be less than 2, right? And so you see this, right? So there's some scope for improvement here. From the max player's point of view, there was one action A1 which gave a value of 3. But now, when he's going to look at, the state C, he knows that, he saw the first action that gave a utility of 2. And he knows that, going further, the value cannot be more than 2. Okay, but here he's already seen something which is 3, and so this A2 action right away, after seeing this node A1 right at C, he can conclude that this is not going to be a desirable action. So he can completely ignore this part. He doesn't have to even get into that part of the tree. Okay, so right, so I hope this point is clear. And again, now once he comes back here to D, right? So now here what's going to happen, he's going to see 14 first. Okay, so yeah, so this is going to be less than or equal to 14. So still there is chance that he might choose this action, because so far the best he saw was 3. Now, so he will get into the next node, which is A2, and which gives a utility of 5. And so he will update this to 5, right? Because this is the min agent. It's going to choose the lowest value. And so here he's not able to improve much. I mean, he'll come here and then he will realize that the value is 2. Okay, and then he will say that, A1 is the best action. Okay, so what happens here is, if you already found some action which gave some value, and later on in the tree, you see that, some part of the tree is not helping you, you can completely ignore that. Okay, so that's what is happening here in this part, which is in red. Okay, so this part of the tree, you don't have to traverse it. Okay, and also, maybe this is not even, that's possible that, you have some other intermediate states and, a subtree. The whole subtree itself, you can ignore it, okay, because of this. Okay, so this is this is just the idea of alpha beta pruning. Any questions on this example?
Ma'am, I had a doubt. In the
Yes,
map,
Prakhar.
like yeah, in the map, like first we give the utilities and then we make the choice, or first we like see what is the utility and then update the choice. Like we got the utilities of B, C, and D, and then we will choose one of them, or first we will first we will go at B and then we will go down, check for it, and then so what is the like use of making the utilities then?
Yeah,
Because we were
so
making the utilities for long trees. So if we are going down and down, then what is the use of making the utilities at the first place?
So these utilities are there for just the terminal states. That has to be there. I mean, it's based on these utilities that you will decide what is the strategy you take. Okay. Now, about this choice of, whether you see all the utilities of these states, like the min values first before making a choice, or you keep updating your choice, right? So that is an implementation choice. Okay, but if you go step by step, uh, then there is some potential to improve. Okay, rather than saying like you see all of these, you compute all the values of B, C, and D, um, and then you make a choice. If you design your algorithm in that way, I mean, it is correct, there's nothing wrong with it, but you will not be able to do this kind of improvements. Okay, whereas if you see that, I mean, even the way we have written the algorithm is in some sense, you keep updating things on the fly, right? Like here, if you see, the algorithm we wrote was you compute the max. I mean, for each successor, like you're starting off this way. You start with v is negative infinity, and you're going on improving it, right? So that's it's an implementation choice. But if you do this, then you can also store what is the best value that you've seen so far, and then you can disregard some parts of the tree. Okay, but I think your question has two parts about whether the utilities are known beforehand, right? And about how the algorithm runs. Okay, so just correct me if that was not your question, or okay,
Yes, ma'am. I wanted to ask that only.
yeah. So utilities, the assumption is that this will be known always beforehand. Okay, and so there are this point, right, about what we discussed on evaluation functions. So if you're going to cut the tree at some point, then I mean, you can treat these as the values given to you by the evaluation functions. So the same idea of pruning, you can do it with evaluation functions also, right? Um, Prakar, was it clear?
Yes, yes, ma'am. Yes, ma'am.
Okay. Yeah. So, yeah, any other questions, doubts about this example or anything of what we discussed now? Is this example clear, like how pruning has helped in this part? Like how what we are trying to exploit here? Is it clear? Okay, you can type or you can ask if something is not clear. Just type if it's clear or not. Yes. Okay. Okay. So maybe I just want to ask somebody who has not responded. Okay. Yeah. What about Ashutosh? Is it clear? Okay. I don't hear any response. Okay. So just few of you have responded. I just want to hear from the rest also. Can you just type if it's clear or not, or what's the thing, or if there's something bothering you? Clear? Okay. 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 All right. Okay. So I think a good number of you are clear with it. So please stop me, okay, if something is not clear. So in this idea of pruning, so I mean, whatever we just discussed now, you can also do it for the min state, right? The same idea, but it's just going to be symmetrically opposite. So what is going to happen is you have a min at the, if you start off with a min state, then what you do is you explore, what is the best here. Okay, so maybe let's just see what happens if instead this was a min and max like reversed, right? So this was 251, and let me just bring it a bit down. And you had D, which was 1452. Okay, and so now the roles are reversed. Okay, you started off with a min, and the second player was a max. Okay, so now the best for at this state. So this is A, this is B. So at the state B, the best is 12, right, for the max player. So the utility is going to be 12. Now here you come back to the the state C. You come back to the min player, and he's going to explore the state C. Okay, so here what is going to happen? He sees 2, and the max player is going to have something greater than 2. Okay, and so the min player has seen 12 is the utility, so this is going to take a value greater than 2. So yeah, he still has to explore a bit more, right? Because yeah, you don't know if this is going to return something. Like if there was a 10 somewhere here, maybe it's going to give you that. Okay, so he has to explore further, and he'll see 5, and so he will update this value to take a value greater than 5 and 1. Okay, so finally this is going to be a value greater than 5. Okay, so yeah, so I think here it doesn't help, but the analogous ideas you can use for the min player also. Okay, like okay, for example, let's come here. Okay, so for the best min you have found here is, so now after this, okay, the value of the state C is 5. Okay, and so the best for the min player is between 12 and 5. Now he's going to pick 5. So the best so far is 5. Best so far is 5 for the min player. And now when he comes to the state B, right? So this is a max state. B is a max state, and 14 is the first utility. So going further, this can only be greater than 14. Okay, and so now the min player knows that the rest of this part, you don't have to explore this, right? Because he has seen something which was better for him, and D is just going to be worse off. Okay, so there's no way that this action is going to be selected, and so he will conclude that this is the best. Right, so the same ideas work for both the max and the min player. So what you do is, to put it down more formally, you maintain a value. So the best value for the max player, so we'll call alpha, is the best value for a max agent. Okay, so the best value seen so far. Okay, so seen so far, and you will keep changing this value of alpha if you find a better and better node. And similarly for the min agent, there is a value called beta. Okay, so which is the best value. So that's why you have this name alpha beta pruning. So best value for a min agent so far. Okay. So there are 2 agents, so it's best value for the max agent and best value for the min agent. And so it's the same algorithm you'll use. So let me just copy this out. I'll just copy the the max and the min value, these functions, because the main function that would remain the same. Okay. So additionally, what you're going to do is you will start off with, you'll have some parameters here. So that is, so let me just put it in red itself. So alpha and beta. Okay. And similarly in the min also, you're going to have these inputs. This is the current best values of the max and min players. Now what you do is, let's write the min value. Let's edit this one first, because maybe this is a little more intuitive. So what did you do? So you had alpha here. So this is the example, right? And the value of alpha was 3 at this point. And what you did is you found a value which is even less than alpha. Okay. So then, you found this, the best value so far from a lower down state was a value less than alpha. So you just ignored the rest. Okay, so what you can do is just put it down here. Okay, so they can have one more step here. So you are getting the value of that state. Now, if this value if the value is less than alpha, then you just return V. Okay, so it's not the exact value of that state, but what it's giving you is this is actually an upper bound. So this is an upper bound on the value of that state, but that is sufficient. You don't have to explore too much to, you don't need the exact value to get the best strategy. Okay? So you do this, and also you need the step of, updating your beta. So beta is the best value for the min agent, and if the best value seen so far is better, so at this point you do all your iterations, and then what you do is you just say beta is just min of V and beta, right? If you found that your value improves, then you just make it better, okay, and then you just return this value. Okay. So similar steps you will do for the max agent, but it's just going to be flipped. Okay, so is this idea clear? How the changes made to the algorithm?
Ma'am, can you explain how beta has been updated?
Yeah. So maybe let me just go back to this example. Right. So so here so initially you set what happens is you will set alpha to be alpha is the value corresponding to the max player. So you set alpha as negative infinity, and you will set beta as plus infinity. So this is the initialized values. Okay, so this you will update in your main function was there, right? The value function which you will start off with. There you will set alpha as negative infinity and beta as plus infinity. And after this, you come. So the way the algorithm proceeds is you start off with A and then you come to B. So now beta is plus infinity. So as you see a better value here, you're going to update your beta, right? So beta is now going to be, so you started off with 3. So you update beta as 3, okay?
We
And
update beta after visiting all the
after
children,
visiting
right?
all, yeah, right, that's right. So you don't have to update beta here, that's right. So so at the end you see all the children, and then you found that the best you saw was a value of 3. So you can just say beta is 3 here. Okay, and so in this case, now when you come back here, so I think maybe there is a difference. You need to update your beta as you go along, right? Because now when you come back to the max agent, you have to update it at this point, right? You will set your alpha as 3, right? So maybe let me, I think this has to come here itself, right? So you update your beta right here. Did you get what the issue was? Right? See, let me just explain this again. So I made a mistake in writing the order. So it had to be like at this point, as you see each of the successes, there you will update your beta. Okay. So because, I'm deriving this because, for the alphas, right? At each point, once you see the first child, you should have your alpha value, and only then you can update, you can make use of the fact that the second child, there's a value going to be less than 2. And okay, so that's the reason why you have to update it as you go along. So here what's going to happen is you will come to this point. Your initial beta was plus infinity. Now you would update it to 3. Okay, you again come back. So alpha is still minus infinity, right? So your value you found here 3 was better than the minus infinity, so you will proceed further. And here you have a value of 12, so that's anyway, you don't change the beta, you don't change the value. And again you find an 8, nothing changes. And then you come back here. Okay, now for the max player, what you have to do is you have to update your alpha. So the value of this state B was 3, and now you update your alpha as 3. Okay, so that's going to reflect here also. Let me just make that change also. Okay, so here what you would do is the symmetrically opposite thing, right? So if, look at this one, if you found a value which is greater than alpha, right? So here, if your V is going to be, sorry, greater than beta, right? You think of the perspective of who is calling you, right? So here, if the value is, the best so far was 5, so this was the beta, right? That was the best for the min agent, right? And at the max agent, what you're going to do is you're going to think from the perspective of who is calling you. Okay, so the min agent is calling you, and his best value was 5. That was beta. And if you found something which was greater than beta, then you don't have to cover the remaining parts of the tree. So if V is greater than beta, you just return V. Okay. Now, at the same time, you update your best. So this is a max agent which is trying to write this function. So what you do is alpha has to be updated if you found something better. So you say alpha is max of alpha and V. Okay. So, yeah. So, okay, so let me just pause for a minute. This ideas can be a bit confusing. So are there any questions on this? Anything you want me to explain again or something? Okay, you're all very quiet. I want you to speak up. Is something confusing, something bothering? Advait, is what's happening?
Yes, ma'am, I've understood it.
You understood it?
But I think I'll like need to write out the code to get a better understanding.
Yeah. So just the way to, get more comfortable with it is just try some more examples. Try to trace the behavior, what happens, as you run this code, this algorithm, what happens. Okay. And yeah, that's when things will get a bit more clear. What about the others? Maybe Tanuja?
Yes, ma'am. I understood it, but I think I need to as other you need to practice a bit.
Okay. Okay. So somebody else, Kunjan?
Yes, ma'am, I understood it.
Understood it. Okay. Uh, just want to ask some more people. Maybe. How about Umang?
Yes, ma'am, it's clear.
It's clear. Okay. What about Tushar?
Yes, ma'am, it's clear.
Also ask maybe Sejal.
Clear, ma'am.
Sejal, you're here?
Yes, ma'am. Can you not hear me?
Yeah, I can hear you now. Tell me.
Yeah, it's clear.
It's clear? Okay. Yeah, so just stop me, okay, if this is confusing, because we went a little back and forth when I wrote the algorithm down. So this might have caused some confusions, but just stop me, okay, if this is something is bothering you. Anyway, you will also implement this in your next lab. So I think that that will make things even more clear as you implement it. And one important thing here is, the values that you return here are not going to be the exact value, right? And see, like for this case, for the the min state, what you're going to get is an upper bound. And in the max state, what you compute here, what you return here is going to be a lower bound. So it's a lower bound on the exact value, like here, right? So for the state D, for instance, it's being led by a max player, and okay, in this case, it's actually even exact. But suppose this value here was say some 21. The value of the state D would have been 21, but what alpha beta pruning is going to give you is this value 14, because it's a lower bound, and that's what mattered to make the algorithm function well and to exploit this fact, the pruning idea. It just needed this value 14 to be returned. You don't have to actually exactly return the best value. Okay, that's something to keep in mind. Also, okay, as a homework, maybe I'll just ask you to try some more depths. Okay, so as a homework, try trees of maybe depth 3. Okay, and see what happens of depth, larger depth. Maybe let's not restrict it to uh, depth 3 alone. So of larger depth, you see, and even there you get, sometimes a whole subtree can be pruned out. Okay, and see how alpha beta pruning works. Okay, so yeah. Okay, so I think with this idea, maybe we'll just move on to a slightly different topic along these lines itself. But suppose your agent behavior. I mean, so all these algorithms, this minmax and all these pruning kind of ideas, which essentially built on minmax, assume that your adversary is going to hurt you all the time. Okay, so I just want to motivate a slightly different kind of agent now. So maybe I'll just show you one demo of Pac-Man itself. Okay, so maybe I'll try this one. So this is another layout that I had. Okay. So here, what I'm going to show you is how, I've coded the minmax agent, and I'm going to show you how it works on, some particular layout when, the ghost is not particularly random. I mean, the ghost is not adversarial, but maybe it's a random ghost. Okay, so let's just jump into the demo. So you see Pac-Man here, right? And there's a ghost here, and there is one food particle. Okay, the ghost is hanging around the food, and Pac-Man is supposed to go and eat the food, but it's a minmax agent that has been coded, so it's just hovering around here. Okay, it's not going close to the food because there's a ghost there. Okay, rightfully so. Okay, but it's doing it for too long, right? The ghost is also moving around everywhere, but still Pac-Man is just staying put. It's just going, it's just juggling between these two locations. Okay, and the ghost has come up, but still Pac-Man is not going to do anything because there's still a possibility that the ghost is going to come here. Okay, so this is some, you can think of it as a configuration where the minmax agent is not going to do well. Okay, because the ghost is actually not out to hunt you. The ghost is not going to hunt Pac-Man. It's a random ghost. So actually, Pac-Man can come and come behind the food. Okay, he can afford to take the risk, but the Pac-Man is like very risk averse, so it doesn't come. And see, now the ghost is coming closer, and that's when Pac-Man will move. Okay, so it's like the ghost is a motivation for it to move. When it comes close, only then it moves. Okay, so this is it's a setup where this is not desirable because the ghost is actually a bad. It's not so bad. Whereas if you had, I'm going to now try a directional ghost, which is an adversarial ghost. So it's going to come. See, now this ghost has come behind Pac-Man. So here this is the right thing to do. You go away from the ghost, and and then you will ultimately hit the food. Okay, so these are like two scenarios, right? So one scenario is where the ghost behaves as you expect it to, and then you are fine. But when the ghost is random, this doesn't help. So that brings me to the next model sort of, so which we'll call as Expectimax. Okay. So it's just a small tweak you need to make to this algorithm. So Expectimax is where the opponent is not a min agent, opponent is random. Okay, so opponent is a random agent. So now what can you do best? right? So suppose let's take the same tree. Okay, maybe it's easier to just draw it again. Okay, so yeah. So you had a start state, then you have so this is A, B, 3, 12, and 8. And so now this is the other state with 2, 5, 1. And then you have D, where you had 14, 5, 2. Okay. So now here as Pac-Man, you are a max agent. You want to maximize your utilities, but the opponent is a random agent. Okay. So what would you do? So I tell you that, the random agent is going to play each of these three strategies with equal probability. Okay. So with probability 1/3, he's going to choose action A1. So this, let's just call everything A1, A2, A3. So A1, A2, A3. Okay. So yeah, so it chooses action A1 with probability 1/3, A2 with probability 1/3, and action A3 with probability 1/3. Is this the probabilities? So this is for the opponent. So opponent has this model. Okay. So then in that case, what should your strategy be? Any thoughts?
We should find the expected value of the B, C, and D, and then go
Right.
for maximum value.
Exactly. Right. So that's the most obvious thing to do. So what is going to be the expected value at the state B?
Average of all the
Average
children.
of these three, right? So yeah, 1/3 of these three. Okay, and in C also you have like 1/3 of 2 plus 5 plus 1, and yeah, and then you get the idea, 1/3 of 14 plus 5 plus 2, and then just choose the max of these three numbers. Okay, and you could have like different models. So sometimes maybe A1, there's more chance of the agent playing action A1. So then you adjust this value accordingly. So maybe something like A1 with probability half, and A2 with probability 1/4, and A3 with probability 1/4, right? So all those things can happen. So then you adjust these numbers accordingly. So you take the expected value at each of these states and choose the max. Okay, so yeah, right. So that is an other agent. Okay, so that's why the name is rightly Expectimax. Okay, so you are the Expectimax agent. Okay, so there's going to be inherent difference in the behavior of these two types of agents, and you can never say that one is better than the other. For example, if you are an Expectimax agent and then you are meeting an adversarial agent, the opponent is an adversarial kind, then this might not be a good thing to do. Okay, there's never a best strategy that you have to take. In some cases, one works well. In some cases, another works well. Okay, so I just want to also show you one more demo on the difference between these two kinds of agents. So are there any questions on Expectimax? It's clear, right? I didn't spend too much time because it's a straightforward algorithm, I thought, with expectations. And you just take the expected value and you maximize.
Yes, ma'am.
Right? Okay, so let me just show you one more demo. So I'm just going to show you, a different layout, okay, where there are going to be two ghosts, and I'll just show you what a min-max agent does and what an Expectimax agent does. Okay, so yeah, this is a min-max agent. So here you see that this is okay. So let me just run it a little slower, maybe. Okay, so what happened is there were two ghosts, and Pac-Man actually moved towards one ghost, right? So the other ghost here was a bit far, and there were these food particles. And I mean, of course, he's going to lose for sure because he's trapped between two ghosts. So there's no doubt about him losing at some point. but maybe there's a possibility of eating these. If this ghost comes down, if the blue ghost actually moves down, then maybe he could have gotten some points. But that doesn't happen with a min-max agent, because it's thinking that the ghost is always going to come after Pac-Man. And so in this case, actually the blue ghost moved down, right? But it didn't happen. But what it thought was the blue ghost is also going to move towards this. This is also going to move towards him. So he just tries to end the game as soon as you can, because one of the in the utilities, there is a penalizing for the longer time you take. Okay, if you finish the game, if you win the game sooner, then you get better points. Whereas if you take more time, there is a penalizing. So that's why it just ends the game immediately. Okay. Now let's just see what an Expectimax agent will do. So you see the Expectimax actually went towards it. So immediately maybe the score would have been worse. See, in this case, the score was minus 502, and whereas minus 501 in min-max. So immediately it did bad. But it's if you run it many times, maybe it's a random ghost which is playing there, then maybe it can improve. For example, let's see now. See, this is actually a better state. It's actually able to eat the dots, and it died. Okay, but it got a better score here. Okay, so that's kind of the difference between these two types of agents. Okay, one is always thinking that everybody is out to get you. Let me protect myself. And Expectimax thinks, okay, the other guy is random. He's not going to hurt me. He's just doing something. Let me do as best as I can. Maybe I can do well. If it's a random guy, if he plays a bad choice, maybe then I can still benefit. Okay, so that's the difference in the outlook of these two. Neither is better than the other, and in fact, you always don't know what kind of agent you're dealing with on the other side. Okay, so yeah, so that's going to be in some sense the next topic, where you have some uncertainties on where you're going to land up. After a state, after you take an action, you don't know for sure what this new state is going to be. Okay, so we're going to look at Markov decision processes starting from the next time. Okay, so I think I'll wind up. Yeah, I think we are short of time also. We are on dot. So I'll end here, and maybe if there are any questions, I'll stay back. If not, thanks everyone. See you tomorrow.